The other half of the test is talking about Markov chains. And so here's kind of an example of Markov chain, some numbers. You've got an initial distribution, which is a row vector. Notice these probabilities, they're numbers between 0 and 1, and they add up to 1. And then you've got your transition matrix. You've got two different things. So make sure you know the difference between a distribution, which is a row vector, and the transition matrix, which is a square matrix. Okay, make sure you know the difference. But that's pretty much all you've got. You've either got a distribution or a transition. So this notation just says, I want to find the probability of going from state 3 to state 1 in one transition. And that's really what my transition matrix is about. Okay, I don't know what the 3 states are, but I do know that there are 3 states. And if you look at your transition matrix, it's showing you all of the probabilities of going from one to another. So if I want to go from 3 to 1, look at your rows first, row 3 to column 1. I'm looking at that number right there. The answer is 0.2. There's nothing much to that problem. I'm finding the probability of going from state 3 to state 1 in one transition. Nothing to it, 0.2. Okay, now, notice it's the same 2 matrices, the same problem, all right? But now I want to find P3. That's the transition showing what would happen after 3, the probability after 3 transitions. Okay, when we talked about a mother and a child and a grandchild and a great-grandchild, we're talking about transitions from one generation to the next. But I'm going to want a calculator for this. So I'm going to take this P matrix, this transition matrix, to the third power. So what was it? 514.5.1.4 433 217. Just double check all those numbers. The rows add up to 1. That looks good. I want to do that matrix, to the third power. Okay. Let's see the decimals. Okay. Decimals are probably easier for us to handle there. 335, 124. Okay. 541. 346132. 522. 308124. 568. That's the transition matrix that shows the probability of transitioning from one state to another in 3 transitions or in 3 generations. Talking about from like a mother to her great-grandchild, mother to child to grandchild to great-grandchild. That's 3 transitions. Okay, so that's what we're talking about. You still have the same 3 states, whatever they are, and that shows all the transitions between those states. So the next problem says probability of going from state 2 to state 3 in 3 transitions. Well, if you look at going from row 2 to column 3, we're looking at this probability right here. That answer is 0.522. That's a good question. All right. It's an easy question if you know what to look for. If you don't know what you're doing, you'll never, ever get there, though. Okay, find X3. X3 is a distribution, okay? It's a distribution. You've got 3 different things, okay? State 1, state 2, and state 3. And the initial distribution says 30% of the whatevers are in state 1, and 10% are in state 2, and 60% are in state 3. That's not talking about transitions. That's talking about the population, and it's describing what is. So X3 wants to know about what does the population look like after 3 of those transitions. In order to do that, you have to use a formula, and that formula is xn equals x0 times p to the nth power. So for this problem, n is 3. You can just say we're going to multiply x0 times p to the third. All right, so x0 is right here. We just did p to the third, but we've got it in our calculator right here. So let's just enter x0, 316. So over here, I'm going to go 0.3, 0.1, 0.6. Okay, I'm going to switch them around just because I want to. And I'm going to go that first matrix times the second matrix to the third power. That's like x0 times p to the third power. And I get this right here. Okay, I'm bumped up to 6 sig figs, so it should be rounded off as much as I need to. Yeah, that's pretty good. 0.3199. One, 2, 4, 8. 5553. That's the distribution, okay? And what that means is, what that's talking about is that's the percentage in state 1 now. That's in state 2, and that's in state 3. So you can see that state 1 has increased a little bit, and state 2 has increased a little bit, and state 3 has decreased a little bit from where we started. Find the equilibrium vector. Okay, the equilibrium vector, there's 2 ways to do it. The shortcut way is to take the transition matrix out to a big power, like 100 or 1,000 or something like that. Okay, sometimes that's hard to do, though. Sometimes that leads to decimals, and we're gonna end up needing fractions. And if you can't change that decimal to a fraction, you're in trouble. Okay, so the concept here that we need is equilibrium vector times the transition matrix equals equilibrium vector. So what we can do here is 0.3, 0.1, 0.6 times this is supposed to equal 0.3, 0.1, 0.6. We've reached equilibrium and nothing changes, okay? So, oh shoot, I messed that up. Okay, hang on. We don't know these numbers, okay? These numbers are actually going to be variables here, okay? We don't know the equilibrium vector yet, so I shouldn't have put 316 in. That doesn't make any sense at all, okay? We want to know what these variables are so that we've reached equilibrium, okay? That looks more like it. So what we do is we take row times columns, and we come up with some equations. So the first one is 0.5x plus 0.4y plus 0.2z equals, this is the first row, first column entry, x. First row times the second column is going to be 0.1x plus 0.3y plus 0.1z equals the first row, second column entry over here, y. First row times third column gives me 0.4x plus 0.3y plus 0.7z equals z. Okay, I don't have a whole lot of room here. So I'm going to do a couple of things here. I want to subtract this x over, okay? And I would get negative 0.5x plus 0.4y plus 0.2z equals 0. I'm trying to get it in standard form. Is what I'm trying to do. And I'm going to subtract this y over here. I'll get 0.1x minus 0.7y plus 0.1z equals 0. Subtract this z over here, and I'll get 0.4x plus 0.3y minus 0.3z equals 0. Okay, so I'm really super out of room here. Also, I'm going to multiply. I don't like these decimals, so I'm going to multiply all of these by 10. So if you do that, we'll have negative 5x plus 4y plus 2z equals 0, and 1x minus 7y plus z equals 0, and 4x plus 3y minus 3z equals 0. But here's the kicker, okay? Those three equations turn out to really only be worth two equations. So you have to add in this extra equation. But we do know an extra equation because we have this extra bit of information. Since this is a vector, since this is a probability vector, we know those probabilities are going to add up to 1. So I'm going to add in a fourth equation, x plus y plus z equals 1, because I know that to be true. I can do a Gauss-Jordan, all right, on this. I'm gonna do a reduced row echelon form on this and see what happens. We've got a 4x4. Top row is negative 5, 4, 2, 0. Second row is 1, negative 7, 1, 0. Third row, 4, 3, negative 3, 0. And bottom row was, 1, 1, 1, 1. Oh no! my hand slipped. I just hit clear. Oh man, that stinks. Negative 5, 4, 2. Ugh. One, negative 7, 1. 4, 3, negative 3. One, 1, 1, 1. Okay, keep it steady now. Keep it steady. Here we go. Got it. Whew, that's tough. Okay, so look down here at the Gauss-Jordan, and we got some pretty gross results here. So 9/28, 1/8, and 31/56. Those are your numbers. That's your vector. So where are we at here? I'm not going to write down the whole thing. Nine 28ths, 1/8, and 31/56. So what that means is in the long run, you'd expect 9/28ths of the population to end up in state 1, and 1/8 to end up in state 2, and 31/56 to end up in state 3. That's your equilibrium vector, and that's what happens in the long run. So then the long-term probability of ending up in state 3, that's an easy question because all we have to do is look right here. Look in your equilibrium vector at state 3.